Hello and welcome back to Chemistry Practice. Today we are going to do a couple of sample boiling point elevation problems. So let's go ahead and look at this equation really fast. I went over this in the last video, but let's remind ourselves what it is saying. And as usual, when you look at one of these equations in chemistry at first, there is a moment of fear. You think, what does all of this gibberish mean? But let's look at each part of it and see if we can make sense of it. This little triangle just means a change in temperature. So the temperature change of the boiling point. We could just replace all of this and say boiling point elevation equals some constant, boiling point constant. This constant will be provided for you in the question or on the test, most likely, unless they're asking you to solve for it. The constant varies based on the solvent. Here the solvent is water, which is the most common solvent, but there are others out there. Notice it is in degrees Celsius per molality times the molality of the entire solution. Remember, molality is moles of solute over kilograms of solution. Solvent. See how easy it is to mess things up in chemistry? And Van Hoff's factor is the I. If it is a molecular compound, if you put it in the solvent, it will not dissociate. So this number will be 1. If it is an ionic compound, it might dissociate. It will most likely dissociate. And this number will represent how many ions it will dissociate into. So if it's salt, this dissociates into Na and Cl. So this is 2 ions. So we'd have to put a 2 here. That depends on the type of solute that you are adding. I think all these problems here have a 1 there, so we're basically going to ignore that. Maybe I'll do a video later that has some Van Hoff's factor numbers in it. So let's go ahead and get started. What is the boiling point elevation when 11.4 grams of ammonia, NH3, is dissolved in 200 grams of water? Well, let's go ahead and write our equation. The boiling point elevation equals the boiling point constant times molality, little m, times Van Hoff's factor. They provided the boiling point constant for us, 0.52 degrees Celsius per molality times molality. This is not going to dissociate, so this will be a 1, so we will ignore that right now. So if we can find molality, we will be set. We can solve this. And as you see, nothing is straightforward in chemistry. Suddenly we have a problem. Molality is moles of solute over kilograms of solvent. We don't know the moles, and we don't know the kilograms. Let's start with our problem up here. We have 11.4 grams of NH3. That is our solute. Is there any way we can figure out how many moles this is equivalent to? And there is. We just have to do a simple conversion. So I go to the periodic table, I look up nitrogen plus hydrogen, I look up their molar masses, and I add them together, and I get 17 grams per mole. So I know 1 mole of NH3 is 17 grams. Now I can divide these numbers. 11.4 divided by 17 grams will give me 0.670 moles. What about kilograms of solvent? Well, I have 200 grams of water. Now I have to convert that into kilograms because that is the solvent. Let's go back and remember King Henry doesn't usually drink chocolate milk. So the U stands for units. The units here is grams, and I have 200 of them. Remember, the decimal point is there. But I need kilograms. So I have to move my decimal to the left. 1, 2, 3 spaces. 1, 2, 3. So 0.200 kilograms. Don't you see how chemistry works? They keep building on what you're supposed to already know. So if you haven't learned some of those previous things well, it can really start to catch up with you right about now. Now we divide this to get moles. We divide this to get molality. And our molality equals 3.35. Now, if we just multiply this, these units cancel, and my answer is 1.74 degrees Celsius. That is how much the boiling point will raise if I add 11.4 grams of ammonia to 200 grams of water. The normal boiling point of water is 100 degrees. So if they ask for the final boiling point, which they don't in this question, but if they did, I would just add these together. My new boiling point is 101.74 degrees Celsius. Okay, we're making some progress. Let's see if we can figure out this next one together. 0.64 grams of adrenaline is added to 36 grams of carbon tetrachloride, and it produces a boiling point elevation of 0.49 degrees Celsius. What is adrenaline's molecular weight? That seems kind of complicated. We have the constant, the value of carbon tetrachloride. So let's go ahead and write our equation. And yet again, we can ignore Van Hoff's factor because it will not dissociate. They are already giving us the boiling point elevation, which is 0.49 degrees Celsius. And they've already given us this constant here, which is 4.95 degrees Celsius per molality. So, we need to find the molecular weight of this. Basically, we need to find what the molar mass of this is on the periodic table, but I don't have the formula. So maybe if I could figure out how many moles of this I have, and I know how many grams I have, I can go back and figure out the molecular weight. Okay, so let's try to figure out molality. I don't know how many moles I have. I'm going to put an X there. It's an unknown. And I really can't figure it out right now because I don't know the molecular weight. If I knew the molar mass and molecular weight, I could figure that out, but I can't. So, do I know how many kilograms of solvent I have? As it turns out, I have 36 grams. So yet again, I'm going to have to convert 36 grams to kilograms, and I will move this decimal 3 places. 1, 2, 3. So it's 0.036 kilograms. Okay. Now, I could sit here and do a little bit of math. I could take 0.49 equals 4.95. Divide this 4.95 by 0.036. And I'm going to get 137.5x. Then I can solve for x. So x equals 0.00356. And then how did I solve for x? I simply divided both sides by 137.5. And that canceled that there. So, this is how many moles I have. I have 0.00356 moles of adrenaline, and I know how many grams I have. Okay. If I think about this for a second, what is molecular weight? If I go to the periodic table and look up like this right here, ammonia, I said it was 17 grams for every 1 mole. Okay, basically, molecular weight is moles per gram. So I know I have 0.64 grams. Or I could reverse it. And I know how many moles I have. I'm sorry, this should be grams per mole, so the gram should be on top. I take 0.00356 and divide that. And as it turns out, I get about 180 grams per mole. That is the molecular weight of adrenaline. So if I figured out the formula of adrenaline, and then I went to the periodic table to add it up, it would be about 180 grams per mole. Wow. That's probably a little bit more complicated than you may get on a test, but if you can do that, you will be set. And I think the key here is always asking ourselves, okay, what is a mole? A mole is grams, or what is molecular weight? Grams per mole. What is molality? Moles per kilograms. So if we have any of these numbers, we can plug them in and try to figure out other things. That's the key. Normally, if you can get to moles, you are good. Okay. Yet again, we're making some progress. Let's head on down to a few more examples. How many grams of fructose, and we see that this is fructose, must be dissolved in 937 grams of acetic acid? So this is obviously the solute, and this acid is the solvent, to raise the boiling point by 9.1 degrees Celsius. And they give us the boiling point constant for the solvent, acetic acid. So let's go ahead, write out our equation. Yet again, I'm not going to write out Van't Hoff's factor. Why is that? Because if I add this to the acid, it will not dissociate. So, they're already giving us this boiling point elevation, 9.1, equals, and they're giving us the constant, 3.08, times the molality. This problem is similar to the one we did a couple of problems ago. We're looking for how many grams of this stuff we have to dissolve in here. So yet again, if I can figure out how many moles of this stuff I have, I might be good. So let's take 937 grams and convert it to kilograms. Yet again, 1, 2, 3. Or I could just divide this by 1,000. So it's going to be 0.937 kilograms. Okay. And we don't know how many moles we have. So, that's our unknown. That's our x. Basically, I can rearrange this 3.08 divided by 0.937. It will give me 9.1 equals 3.28x. I'm going to divide both sides by 3.28. 9.1 divided by 3.28 equals 3.28 divided by 3.28x. So, x will equal 2.77. What does this number tell us? Basically tells us how many moles we have. We have 2.77 moles of fructose. But we also have the formula here. So I can figure out how many grams of that equals I have 2.77 moles of fructose, how much does 1 mole of this stuff weigh? I'm going to put that on bottom, 1 mole. Now I have to go look C6H12O6 up on the periodic table. I have to look up the molar mass. So I look up carbon, I multiply it by 6, hydrogen multiply it by 12, oxygen multiply it by 6. And I end up with about 180 grams, which is just a coincidence that that was in the last question. Now, with this simple little conversion, 2.77 times 180 grams, I would get 499 grams. So I need 499 grams of this stuff to be dissolved in 937 grams of acetic acid to raise the boiling point by that much. Whew, that seemed like a lot of work. And sometimes you get multiple choice tests. If you have that, you can just start plugging in numbers. That just makes life so much easier. But if you have free response questions, you still got to know how to do it. Moving on down. A 166.5 milligram, let's keep that in mind, sample of the compound eugenol was dissolved in 1 gram of chloroform. What is the molar mass? This question is similar to the one we just did 2 questions ago. It's asking for the molar mass, the molecular weight of this stuff. We don't know the formula of eugenol, so that's a problem. Well, let's write our formula. The boiling point elevation equals the boiling point constant times molality and times the Van Hoff's factor. But, yet again, this will not disassociate. So Van Hoff's factor is 1, so let's ignore it. They give us this boiling point right here, which is 3.68. The boiling point elevation, 3.68. They give us the Kb, which is 3.63. Yet again, we do not have the molality. We don't have the moles. But we have a 166.5 milligram sample of this stuff. 166.5 milligrams. Okay, let's go back to King Henry doesn't usually drink chocolate milk. Our units are grams. We need kilograms. Right now we have milligrams. We have 166.5 milligrams. So how many times do I have to move the decimal place here? I have to move it 1, 2, 3, 4, 5, 6. That seems like a lot. So, actually, I'm making a big mistake right here. And this is a good thing to point out. Sometimes halfway through a question, you realize you're doing it wrong. I have 1 gram. That is how much of my solvent I have. So I have to take my 1 gram and convert it to kilograms. I'm sorry. So that makes life a lot easier. We'll just take this decimal and move it 3 places. 1, 2, 3. So it's 0.001 kilograms. Wow, I'm so lucky I caught that. At this point, I really don't want to do this whole video over again. Now, we can rearrange everything just like before. 3.63 divided by 0.001. So I'm going to get 3.68 equals 3,630x. So x equals 3.68 divided by 3,630, which is this little small 0.010137774. It's this little number here. Okay, now, yet again, molecular weight, molar mass. See how they like to change up the terminology just to confuse you even more? Is grams per mole. Well, I know how many moles I have. I have that many moles. Do I have to write it again? I guess I will. So how many moles I have? How many grams of this stuff do I have? I have 166.5 milligrams. And I just have to convert it to grams. So let me show you that again. Back to King Henry. King Henry doesn't usually drink chocolate milk. If you get good enough, you can just do this in your head, but I just want you to visualize how you can do it if you don't want to do it in your head, if you can't. I always hate that when people just throw the number down and they just assume you know what's going on, and they just move on, and you're like lost. So, we have milligrams, 166.5 milligrams. I need grams. So I'm going to move the decimal 1, 2, 3. 1.1665 grams per mole. So if I take 0.1665 grams, divide it by this big, actually small number, I get 164.2 grams per mole, which is about the molar mass of eugenol. I'm probably mispronouncing that, but I'm not redoing the video now. Okay. I do have another problem, but to be honest, it's exactly the same as a couple of these other ones. So we've done 4 problems. They have different permutations, which means different variations of what you can do. I think we've actually done a couple of the harder problems. If you're doing just sort of basic chemistry in high school, they're just probably going to give you a little simple problem and not even make you find the molar mass. But if they do, now you know exactly how to do it. You know how to use this equation and be comfortable with it. So yet again, if you have any questions, let me know. Sorry, I forgot one thing. If this is for freezing point depression, this equation is exactly the same. And we put in the numbers exactly the same way. Except this will be a little f. And they're going to give you all the same information, but now it's just freezing point depression. So now you can solve freezing point depression and boiling point elevation problems on the test. Go get that A. Thank you, and yet again, if you have any questions,